Okay, if you've ever struggled with electromagnetisms, you've definitely had this moment. You just finished learning about the electric field, and then suddenly you're hit with another field called electric flux density. It feels redundant, right? Like, why do we need two? Well, in this explainer, I'm going to show you why it's not just another variable. It's actually a brilliant shortcut that makes some really difficult problems surprisingly simple. So let's just tackle the big question head on. Why isn't the electric field, our good old E field, enough? We know it describes the force on a charge. So what's the deal with adding another vector field? It's a totally fair question, and the answer, well, it really gets to the heart of what makes physics so cool and elegant.
You see, the problem is that the E field is kind of like a chameleon. Its value actually changes depending on what material it's in. A point charge will create one E field in a vacuum, but if you put that same charge inside, say, glass or water, you get a different, weaker E field. This dependence on the medium just makes our calculations messy. What we really want is something that just depends on the charge itself, period.
So here's our game plan. First, we're going to really lock in on the exact problem with the E field. Then we'll meet our hero, the D field, and its secret weapon, Gauss's law. After that, we'll actually solve a problem with it, talk about the one gotcha that trips everybody up, and then we'll wrap it all up with 3 key takeaways you will not forget.
All right, section 1, let's dig in and really understand why the E field just can't do the job on its own.
So here's the bottom line. The E field is all about the effect. It's the force that a charge would feel, and that effect naturally gets altered or dampened by any material you stick in the way. So to find the E field, you always have to ask 2 questions. What's the source charge, and what material is it sitting in? Wouldn't it be nice to have something where we only have to ask that first question?
And that right there brings us to the hero of our story. Let's introduce this awesome solution to our medium dependency problem, the electric flux density, or as we call it, the D field.
So here it is. Think of the D field as a pure, direct representation of the charge's influence. It's like you're just drawing lines of influence straight from the source charge, and the density of those lines tells you the field's strength. And its superpower? It totally ignores whatever material is in its way. D gives us a direct link to the cause, not the effect. Now, to make this idea really, truly stick, let's step away from the abstract world of fields for a second and think about something we've all seen, a simple garden sprinkler. You know, this sprinkler analogy works perfectly. The sprinkler itself, that's our point charge. The total water flow coming out, say gallons per second, that's the electric flux. Now, the wetness of the ground, how much water lands on a certain area, that's our flux density, D. And the actual force of the spray hitting you, that's the E field. Now here's the key. Imagine you put a big sponge on the ground. The amount of water hitting the top of that sponge, our D field, hasn't changed at all. But the force of the water coming out the bottom of the sponge, our E field, is way weaker. The sponge, which is our material, changed the effect, but it didn't change the source one bit. Okay, so now that we get the D field, let's see how it unlocks one of the most powerful and honestly beautiful shortcuts in all of physics, Gauss's law. At its core, Gauss's law is really just a simple accounting rule. It says if you imagine putting some kind of container around a bunch of charges, the total amount of flux poking through the surface of that container is exactly equal to the total charge you've trapped inside. It's this incredible direct link between the source and the field it creates. So what does that mean? It means if you can figure out the total flux going through a surface, you instantly know how much charge is inside. Or, flipping that around, if you know the charge inside and the setup is nice and symmetric, you can easily calculate the flux density on the surface. It's just an incredibly powerful accounting tool. Let's go back to our sprinkler. It's like this. If you put a bucket upside down on your lawn, the only water that's going to collect inside that bucket is from the sprinkler heads you actually covered up. Any sprinklers outside the bucket's rim, they don't add a single drop to the water inside it. And that, in a nutshell, is Gauss's law. Only the enclosed sources matter. Theory is great and all, but let's make this real. We are going to use Gauss's law to solve for the D field from a single point charge. This is pretty much the most fundamental problem in all of electrostatics. So here's our mission. We've got a charge, Q, and we want to find the strength of the D field at any distance r away from it. Now, instead of wrestling with some complicated integral from Coulomb's law, we're going to use the elegant shortcut we just learned. We're just going to follow these 4 simple steps. First, we draw our imaginary container, our Gaussian surface. Since the problem is all about a point which is spherically symmetric, a sphere is the perfect choice. Second, we just apply Gauss's law. The charge enclosed, Q enclosed, is, well, it's just Q.
Now for the third step, and this is the magic part. We use symmetry to basically kill the hard calculus. Because we chose a sphere, the D field points straight out everywhere, perfectly aligned with our surface. And since every point on the sphere is the same distance from the charge, the magnitude of D is the same everywhere on our surface. This makes the math incredibly easy. So that complex-looking surface integral from Gauss's law, it just becomes the magnitude of D times the total surface area of our sphere. And we all know the surface area of a sphere is just 4 pi r squared. So, just like that, our big, scary calculus problem turns into simple high school algebra. And when we solve for D, we get our answer. The electric flux density is just the source charge Q divided by the surface area of the sphere, 4 pi r squared. Now notice what's missing here. There's no epsilon. There's no mention of the material whatsoever. It's pure, it's simple, and it only depends on the source charge and how far away you are.
Okay, now it's time to tackle the number one point of confusion. What is the exact relationship between D and E? They are definitely related, but they are not the same thing, and it is absolutely crucial to know the difference.
Let's just put them side by side. Think of D as the pure flux density radiating out. That's why its units are coulombs per square meter. It is all about the source. But E is the force field. It's what you'd actually measure or feel, which is why its units are newtons per coulomb. It's all about the effect, and that effect is always shaped by the medium it's in. The bridge that connects these two fields is this beautifully simple little equation, D equals epsilon times E. That little Greek letter epsilon, the permittivity, is just a property of the material. It tells you how that medium translates the fundamental D field into the force-related E field. In a vacuum, we call it epsilon naught. For any other material, it's just epsilon. If you need one sentence to remember this for the rest of your life, this is it. The charge creates a D field. That's the cause. Then, the material around it reacts to that D field and determines what the resulting E field, the effect, is actually going to be. Whew. Okay, we have covered a lot of ground. Let's boil it all down to the 3 most important things you need to walk away with from this explainer.
Okay, let's lock this in. Number 1, D is all about the source charge. It could not care less about the material. E is all about the force you would feel, and it absolutely depends on the material. Number 2, Gauss's law is your best friend. It is the ultimate shortcut. For any problem with symmetry, it lets you find D with basic multiplication. And number 3, the link is always D equals epsilon E. If you know one, you can find the other as long as you know the material.
And I'll leave you with a final thought to chew on. This really powerful idea of having a fundamental cause field that's generated by a source, and then a material-dependent effect field that actually produces a force. That pattern isn't unique to electrostatics. It actually repeats itself throughout physics, especially in magnetism. So, next time you see 2 fields that seem related, ask yourself, which one is the cause and which one is the effect?